Hey guys, so I'm here to talk to you today about ring modulation, and we're going to show you a ring modulator that I built. This is from my Eurorack setup, and it looks like this. This is from Eurorack Hardware, EH, and as you can see, it's a dual unit. It has a signal in, it has a carrier in, and it has an output, and then the same thing on the bottom. So there's two ins, two outs to this. So I can run two channels of ring modulation. Now on the back side of it, well, you can see kind of the jacks are there mounted to the circuit board, and on the back are four transformers, one for each input and one for each output. And then here you can see the other active components, which are these rings of four diodes. So the input signal comes in to one of the transformers, and it goes to this ring of diodes. That carrier signal comes in and enters the ring at the two corners, and then it manipulates the audio signal, and then that goes through the output transformer to the output jack on the back. So very simple passive component. You don't need any power for this. It runs completely off of diodes and transformers. So let's check it out. Okay, sweet. So we're set up to start working here. And just a little quick run through here. I have a MiniBrute 2S here. Down here is a keyboard sequencer section. I have a note here, or I have a scale. It also has an arpeggiator and sequencer, but we'll get to that some other time. Anyway, I have a couple of notes here, and just to show you what I have. This is oscillator 1. It has a sawtooth, has a square, has a triangle. We have a noise source. We have an external input. That's all passing through a filter and then out the amplifier and through the master volume. Now, I'm going to just use the sawtooth for this experiment. In addition to that, I have an oscillator 2. And oscillator 2 shows up here on the mixer. It has three waveform choices: sine wave, square, or sawtooth. And we're going to use that. So I'm going to start by just tuning the oscillators. So we'll start with oscillator 1. I'm going to tune oscillator 2 to be an octave higher. So I'm trying to eliminate the beating or get it to be as slow as possible. Now that I've done that, let me tune oscillator 1 up an octave so they're at a unison. And we have a very slow phasing going on because they're almost perfectly in tune. Now, I'm going to show you the ring modulator. Here's the ring modulator I showed you before. And I'm going to hook it up. So I'm going to take the sawtooth output of oscillator 1, plug it into the signal input. I'm going to take that's with the blue cable. With the red cable, I'm going to take oscillator 2 and plug that into the carrier input. Signal or carrier is pretty interchangeable in this application. They're both audio waves, so it's not going to matter. And we'll take the output, and we'll use a purple cable for that, and that's going to go to the external in of the mixer. So here is oscillator 1, oscillator 1, oscillator 2, and here is the external in. oscillators, and here's the ring modulator. Okay, now these are perfectly in tune, but listen to what happens to the ring modulator as I change the tuning. So you remember the oscillator 1 down here is down an octave. Oscillator 2 up here is an octave higher. And then when we add the ring modulator, we're getting the sum of their frequencies, and we're getting the difference. Now, this is a G. Let's say it's roughly 200 hertz. That would make this 400 hertz. And that would mean we would add their frequencies and get 600. We would subtract their frequencies and get 200. Now, we're getting some interaction between the various harmonics. So the external sound is not a pure tone. If I had two sine waves available, I could get exact tones, but that's the basic idea. We're getting both a sum tone and a difference tone. The addition of their frequencies and the subtraction of the lower frequency from the higher frequency. So I want to take a quick look at the schematic for a ring modulator. And if you just look at the big picture here, we have a transformer labeled A on the left. We have a ring of 4 diodes labeled B in the center. And we have another transformer labeled C on the right. Now, a transformer is a device that has 2 coils of wire. And the 2 coils do not touch, but they share a core of iron. They're wrapped around an iron core. And what happens is when you put electricity through a wire, you get a very slight amount of magnetism. If you coil that wire, you get a stronger magnetic field. And if you put an iron core in the center, you'll even intensify that more. Now, the other thing that happens is when you put a wire in a magnetic field, if that magnetic field is changing, you can get a tiny bit of current. And if you take a coil of wire and put it in a magnetic field, you will get a much bigger amount of current. And if that coil of wire happens to be wrapped around an iron core, you can get the maximum amount of current. So essentially what happens is, if signal comes in at the input, which is above letter A, and it's a DC signal, like a constant 5 volts, no electricity will pass across from the primary coil to the secondary coil. But if it's an alternating current, as an audio signal is, the electricity goes back and forth in the primary coil of A. That creates a changing magnetic field. That magnetic field induces a current in the secondary coil. So that's how a transformer works. Now in this case, we're going to apply the carrier signal to the input that's to the left of B. So while we have a signal coming into A, we're also applying a signal at B. And what happens is, if the signal that's coming into the left of B is positive, that's going to cause the electricity to flow one way through the secondary coil, and that's going to get to the diode bridge, the diode ring. If that signal is positive, it's going to flow through the top half of the diode ring. If that signal is negative, it's going to flow through the bottom half through the diode ring. Now, a diode is a device that only allows electricity to flow one way. The other interesting thing about B is that when B is close to ground, very little signal is going to flow through. And as an audio signal at B goes through its cycle, it will sometimes be positive, sometimes be at or near the zero line, and sometimes be negative. So the effect of the carrier signal at B is it's going to raise and lower the volume of the signal at A. That's all going to pass through the diode ring and get to the secondary coil of the output transformer on the right. And that amount of electricity is going to induce a magnetic field, and that magnetic field will in turn induce a current in the primary coil. So the electricity is going to flow back and forth through the primary side of C, and that is our audio output at above C. So it's a relatively simple device. It requires no external power, and it is the design of the ring modulator that I showed you. So we were talking about sum and different tones, and they are literally that. They are the sum of the input frequencies and the difference between the input frequencies. Because they're both audio frequencies, the distinction between carrier and signal is not all that crucial. In fact, you can swap the signals and get the same result. But here's how it works. Let's say we have a signal in blue here at 300 hertz. We have a carrier signal in red here at 100 hertz. We add 300 and 100, we get a sum signal at 400. We subtract 100 from 300, we will get a difference signal at 200. So the two inputs come into the ring modulator, and we get the purple and the yellow tones as outputs. If you mix everything together, you'll hear all four tones. Here's another example. In this case, the signal's at 500 hertz, and the carrier is at 100 hertz. The difference between them is 500 minus 100, or 400 hertz, and the sum of the two signals is 500 plus 100, or 600 hertz. And again, we have our two input signals as red and blue, and what we will get at the output of the ring modulator are the purple and yellow signals mixed together. So in this chart, we have an example of how the sum and difference tones track the signal. So we have a red line that represents the carrier signal at middle C. That's 261.63 hertz. And we have a blue line that represents the input signal, and that's going to go up by various intervals. At the left of the graph, we see the blue line and the red line are together, meaning they're in unison, the same frequency. And when you take those frequencies and add them together, you're going to get double the initial frequency. So the purple trace shows us the sum at about 520 hertz. At the same time, when you subtract 261.63 from 261.63, you get 0. So we will not hear the difference tone at the left of the graph because it has no frequency. Now, as we start going up, as the signal starts going up on the blue trace, we start seeing the sum and difference tones are going to go up, and they're going to go up by the same amount of frequency as the input signal. So if you look at the left of the graph and you see the spacing of the yellow and blue trace, that spacing stays exactly the same. As the blue trace goes up, the yellow stays parallel to it. The same is true for the purple trace. It's always 261 hertz above the blue trace. And as the blue trace goes up, the purple trace goes up by the same amount. So if you look on the right, you see those three traces, sum, input signal, difference tone, are all evenly spaced, and they're spaced apart by whatever the frequency of the carrier signal is. And as noted, the description as the frequencies get higher, the pitch spacing between them gets closer together. So here's our unison. I'm going to drop oscillator 1 an octave. Tune it up. Let's hear the ring modulation. So that's producing nice unison notes that fit with the low tone here. I'm going to now just listen to the ring modulation, and let's bring the tuning of oscillator 2 up and create a different interval. And you notice it gets kind of rattly here. And at a certain point it reaches a sense of stasis, right? It kind of sits and rests into a pleasant interval. Let's see what's going on here. I still have my G here. I have an octave and a minor third. So this is like the 2nd and 7th harmonic, and it's producing the sum of that, which is the 9th harmonic, and the difference, which is the 5th harmonic. So it's a really interesting chord here. If that's a G, then this would be an E flat 7th chord. Kind of a strange combo, but it works. Let's do it again. All right, and again, it's slowed the beating. Still G. That's now a B. So it's a 10th or a major third and an octave. And it's producing a low tone, a root, and a 5th above it. So I have a G major triad. Let's try it again. There's an octave and a perfect 5th between them. And I'm getting very nice thick sound when I add the ring modulation in. Let's try some more. I'll leave these in. You can hear this move. Well, that's kind of interesting. So that's like the 2nd and 7th harmonic. Here's a major 6th and an octave. Getting some weird kind of tones in there, but you can hear we're getting some unusual combinations. Now these are 2 octaves apart, so 1 and 4, and we're getting a difference of 3, and we're getting a sum of 5. So you get some interesting combinations. We can also take a quick look at what happens when we tune a unison. So let me do this again. So they're an octave. Let's go at intervals below an octave. sixth. A perfect fifth. That's a tritone. But this is the third and seventh harmonic of that low E flat zone. Perfect fourth. Major third. Minor third. And then back to the unison. So I'm going to take this white cable for a second, and I'm going to dead patch oscillator 2. And all that means is I have nothing going to the pitch input of oscillator 2. And let's hear what that does. Let me turn off the ring modulation. So here is oscillator 2 by itself. Here's oscillator 1. Here, let's tune these together. So oscillator 2 starts in tune, but oscillator 1 is moving independently of 2. Now watch what happens when I play my sequence. Let's find a better note for oscillator 2. To the ring modulation when we keep oscillator 2 fixed. Because oscillator 2 is not moving and it's oscillator 1 moving, the relationship between the sum and difference tone is constantly changing because the relationship between the two source tones are changing, so we're getting different textures here. That's pretty cool. But we can also try different intervals. With this particular technique, it sounds better in my ears to have oscillator 2 be higher than oscillator 1. We're not actually hearing oscillator 2, because that would be boring. But what we're hearing is the modulation that's happening when oscillator 1 changes pitch relative to oscillator 2. All right, for the next trick, though, I thought it'd be interesting to take an LFO. We'll take LFO 1, and I'm going to just route that to oscillator 2. Let's hear oscillator 2 by itself. And it's going from super high to super low. That's kind of boring. So what I'd like to do is attenuate that. Bring the range of the LFO signal down. So I have an attenuator here on the board, attenuator 1. So I'm patching with the yellow cord from LFO 1 to attenuator 1 in. I'll take attenuator 1 out and plug that into the VCO 2 pitch. And I'm going to dead patch the filter because attenuator 1 normally feeds the cutoff. So I'm just going to plug something in here so the cutoff doesn't move. So I've dead patched the cutoff input to the filter. Let's hear oscillator 2 by itself and bring up the attenuator. So you can hear I have a triangle wave. It's going up slowly, coming down slowly, going up, coming down. Let's bring in oscillator 1. We're not going to listen to oscillator 2. That's just my modulator. Instead, let's listen to oscillator 1, and we'll bring in the ring modulation. So by modulating oscillator 2, the character of the ring modulation is constantly changing. Now, another cool thing we can do is change the waveform. So I have a sawtooth wave that will start high and ramp down. Let's hear that. So here's oscillator 2. I also have a square wave for my LFO, so it's going to start high, and then it's going to jump to low, and then go back to high. I even have a stepped random LFO. But rather than have it change once per sequence, let's speed this up a bit so it's every other note or so. And we have a smooth random as well. So here's oscillator 2 by itself. So a cool thing we could try is let's pull out the dead patch and let this attenuator both feed the amount of LFO going to the VCO, but also feed that LFO to the cutoff. So cutoff will track oscillator 2. So we get this. And let's hear that. So I have a random filter on my low tone, and let's hear that with a ring modulation. Can even add a little noise to that.